Reinforced cement concrete slab design in Freecad. The slab is of dimension 7 meter by 4.5 meters and a thickness of 150 millimeters, and material properties are applied with safety factors M20 concrete and Tata Tiscon Fe500D steel. All four sides of the slab is in fixed boundary condition, and the total design load of 13.5 kilonewton per meter square is applied on the slab. This is including self weight. And then mesh of size, element size, maximum element size of 150 millimeter is applied, and then static analysis is done. After the analysis complete, the results are exported to VTU file. Export to VTU. The Paraview can open these VTU files. First of all, we will open the design file. After opening, we will see it like this. So this is our slab. First, we will apply a clip filter. So these are the clip type box, and these are the controls that specify the bounds of the clip or define the geometry of the clip. So this is along short span on the mid section of the slab of around 1 meter width. Okay, then we will apply a slice. For the meantime, we will hide the total slab. So this is the clip that we are working on, and we will take a slice at the center of the slab section. So these are the parameters defining the location of the slice. If we hide the clip, we will see we will have to take the reinforcement ratio x, because this is along the x axis. As you can see, short span is along the x axis, and here what happens is the reinforcement ratio is varying along this cross section, but we need to locate a center of mass or center of gravity for the distributed nature of the data. So for that, we will use a calculator, and we will calculate the reinforcement ratio into its z coordinate, that we will term it as Rxz. So after that, we will sum everything, sum these values. This is summation of, this can be called as first moment of area, like that, first moment of area. This integrate variable filter will summate all the data, and we need to divide that data by the summation of area. So that's first moment of area is divided by the summation of reinforcement ratio x of this area of this slice. Then we will get the location of the concentrated the center of mass from the bottom of the slab, that is y location. So here in this for this slice, we will see the reinforcement ratio of 220 reinforce. This is not a ratio, this is total reinforcement actually. All the variables are multiplied with its contributing areas before summation. This is done by Paraview software, and the total area of steel is 227.671 millimeter square, and the center of gravity or center of mass is 14.9 millimeter from the bottom. So this is the this type of data we will get from each slice. Okay. If we want to calculate reinforcement ratios along every location in this slab, first of all we have to move from end to end in each strips. So if the clip location changes, like the next strip, okay, in that strip we have to calculate reinforcement ratios. This will be 4500. Okay, like this the reinforcement ratio varies at every location. So in order to capture every detail, I have written a script for short span. I am not running it, I will show you. Wait. For short span there is a script. What this script does is it will go into every position of the clip. It will move the clip to the positions that we required. Like there are 7 strips, 7 clips in this case, because of 7000 millimeters, and then in each clip, for every 100 millimeters a scan will be done, capturing reinforcement ratio, its center of mass, and presenting it and writing it to a CSV file. Okay, where is this? The CSV file. So these are the results. Short span width section from 0 to 100, 0 to 1000, and next 1000 to 2000. Like this we will get the results as a CSV file. After we get the results as CSV, we will take them to any spreadsheet calculators. Like in this case, this is LibreCalc, free and open source. This is long span, this is short span. Short span with width from 3000 to 4000. This is exactly the center strip. As you can see, the reinforcement demand at the edge is higher and it will go down at some point around 1000 millimeters. It will rise up again, and this is exactly the center spot. So this spot here you can see the area is 200 above 200 to 50 millimeter square around. So like this we can visualize the data, and this is the center of mass at every slice. See, at the center where we need to place the rebar is location is around 20, I mean 20 or 14, as we seen earlier, that was 14.9, 15, 20, like that it will varies for every slice. We in reality we can't do exactly like this. Just place a place it like at 20 mm or something with the cover to the concrete. We will place the rebars. So we can consider that this is the position that requires reinforcement at the bottom of the slab, and this portion above the half width of the slab, the above section is the reinforcement where the top reinforcement is required, locations where the top reinforcement is required. So as you can see in this case, in the slab design, what I have done is, let's consider this central strip. As we can discussing, as we already discussing, see, from 500 to 1500 I am giving the top layer at 10 mm at 140 mm center to center, because in this short span I am overlapping the demand is for around 1000 millimeters, but I am overlapping it to 1500 to ensure safety. Up to 1500 the top reinforcement should run along, and the area required is around 533 millimeter square. That will satisfy this 10 mm at 140 mm will satisfy that demand. Likewise, in the bottom portion the highest demand is around 250, as you can read it from the graph. 226 at the midspan 2500, it is around 226 like that. So at the bottom layer 10 mm at 250 mm center will accommodate this reinforcement demand. Like this, every section width of short span is calculated, and this presentation is made here. As you can observe, the edges will require less reinforcement. As we go towards the center, the reinforcement requirement will increase, and next outwards towards the edge the demand will decrease. This is top layer reinforcement, and this is bottom layer reinforcement. Likewise, in the same way as we calculated for the short span, we will calculate that to the long span. In this case, we are considering a 1500 millimeter width section. Okay, as you can see, from 0 to 1500 one section is calculated to just to make it make our work a little less. That's why. So this is the top reinforcement. In here also similarly, this is the long span. As you can see, the top reinforcement demand is ends at around 1000, but we are continuing it to 1500 to ensure safety. That's the reason. And the bottom will run along the entire length. It will not just be located in this portion. It will be run along full length. One more thing we can observe is that at the end sections like 3000 to 4500 of the long span, you can see the Y location, I mean the center of mass is around at 60 millimeters from the base of the slab, but this is, even though it is mathematically or analytically this is correct, according to numerical calculation this is correct, but to consider practicality we will just provide at the 20 millimeter depth height. And also another thing is that, as you can see here, we have given 8 mm at 500 mm center to center, but practically there are some limits of maximum distance between rebars according to several design codes like Indian standards or any other codes. There are some restrictions for the maximum distance between the maximum spacing between the bars. So this might be around limited to 300 millimeters or 3 times the effective depth of the slab, or like that. So this is not according to, this design is not according to the any standards, because this is just an example to show the possibility of optimal designing with finite element analysis and using some open source softwares or free softwares.